we are discussing different modes of input-output data transfer. We have already seen the programmed data transfer. We were in the midst of discussion of interrupt-driven data transfer. We discussed the case of a single device. Now let us see that instead of a single device, if there are more devices, then how to tackle. Okay. Here in this plate, this is over, and we are here. We'll come back to this slide. Okay. Now, one simple solution to more devices is to make the CPU with more number of interrupt lines, okay, interrupt inputs. Instead of only one interrupt, INT here, let there be INT 0, INT 1. Here I have shown a CPU with say 8 interrupt lines. And say each device can be connected to one of these interrupt lines, say device 0 to interrupt 0, device 1 to interrupt 1, and so on, as simple as that. This is interrupt request, and this is interrupt acknowledge. Now comes the situation, say here, say device 0, device 1, device 7, say out of these 8 devices that is connected on say 8 interrupt lines, if more than one device has requested interrupt within an instruction cycle, then what happens? Now naturally, therefore, we'll have to define certain priority. Okay. Now amongst these 8 lines that have been given, we can define a priority. That's say interrupt line 0 will have the highest priority, 1 the next priority, and possibly interrupt line 7 will be the least priority. That means if more than one devices are simultaneously interrupting the central processing unit, and here the simultaneous word is essentially within the same instruction cycle. If they are interrupting, then amongst them the highest interrupt will be acknowledged. Okay, and since the highest interrupt will be acknowledged, it will go to the corresponding interrupt server, interrupt handler. And as I said, that interrupt handler, the first thing it does is that as it's moved to the interrupt handler, the first thing it does is that interrupt is disabled. Therefore, until and unless that interrupt within that interrupt handler is enabled, all other interrupts will remain pending. Okay, till that interrupt is properly taken care of by the central processing unit, by the program in the interrupt handler, no other interrupt will be entertained. But if you wish, if the programmer wish, okay, then actually the interrupt can be enabled once more, and in that case, the rest amongst the pending interrupts will be taken care of. Therefore, this is one aspect. That is why I say that there can be interrupt within interrupt. Okay. Another is, for example, since there are more devices are there, what will be their interrupt handlers addresses? One thing is this, that one can be done is that corresponding to each interrupt lines, we can keep a fixed address that interrupt handler will start from that fixed address. Okay, for interrupt 0, there will be fixed address. For interrupt 1, there will be fixed address. For interrupt 7, there will be fixed address of the interrupt handler. Therefore, which interrupt is acknowledged, the control will go to the corresponding interrupt handler at that fixed address. Okay. Another is that can be done, and which will be essential, as we'll see later on. Okay, as we add more devices, that the device itself, that means by when I say device, essentially the device interface I'm talking of, the device interface itself will, through this data bus, will provide the address of its own interrupt handler, and that is more logical. Okay, so for example, you have many devices, then it's better that on getting an interrupt acknowledge signal, the interrupted device, the device that is interrupting and whose interrupt has been acknowledged, sends first the address of the interrupt handler, okay, to the CPU, so that execution of the interrupt handler at that address starts. This is called vectored interrupt. Okay, and we'll have some more discussion on that vectored interrupt handler. Okay, this is one way naturally of tackling more than say one devices. Right. Now here, let us see that one thing, let me clarify in our processor status word, we have kept one interrupt level bits or the mask bit. Okay, let us talk about that mask, right? So we can keep a mask bits, okay, here, which will tell the status of the different interrupt inputs here. Okay, for example, if the mask bit is 0 here, which means that this particular interrupt line is disabled. If the ith mask bit is 1, okay, then that particular interrupt say is enabled. If it is 0, then it's disabled. Therefore, we can say that these mask bits will tell that what are the interrupts here the CPU at an instant of time has kept enabled or which are kept disabled. Okay, this is one way of controlling that which interrupt will get serviced. Right. Of course, that enable interrupt or disable interrupt is an overriding control that if you disable interrupts, then all interrupts get disabled except possibly some unmaskable interrupt, which we'll talk later on, okay, that unmaskable interrupts. This is one way of tackling. Another is at interrupt level, okay. That means, for example, if there are 7 interrupts and the present level is 3, then all interrupts which is priority wise higher than 3 can only interrupt, rest cannot. Therefore, either one can design the mask bits or one can think in terms of an interrupt level enabling level that above which the interrupts are honored and below which or equal to which the interrupts are not honored. Okay. Therefore, these are 2 ways that we can tackle that interrupts, multiple interrupts, right? Now, this is one way of accommodating more devices. There is another way of accommodating more devices. Okay. This is, so here we have assumed that there is only one interrupt line. This is called daisy chained interrupt acknowledge signal. Let us see the situation, what happens here. Even so, for example, you have assumed that only one interrupt request input is there in the CPU, right? Say and there are many devices that is connected, right? That 0, 1, say I have assumed here k devices have to be has been connected. Now, any IO device which wants to interrupt the CPU, he just puts that interrupt request lines, okay, the signal to the interrupt request line. And this is what we call that word OR. That means this is an ORing. If, so for example, this device, say 0, 1 and kth device is willing to interrupt, in that case, this line will be 1, okay, right. Now, the situation is that how the CPU, which definitely cannot handle all the interrupts simultaneously, it has to handle sequentially, right? The sequence decides upon the priority, etc. That interrupt acknowledge that comes from the CPU is what we call is daisy chain. That means it comes into the first device, there is a gate, then it goes to the second device, there is a gate, and so on to the kth device. Now, the situation says that this device has interrupted. The device which has interrupted will immediately make this interrupt and acknowledge switch off. That means it will open it. So this has interrupted, wants to interrupt. This does not want to interrupt. That means there is no reason that the device should interrupt. Then this is closed. Okay. So for example, we have closed it here, right? And say this also wants to interrupt. Okay, and therefore this is open. Now let us see what happens. That interrupt acknowledge comes, right? It is stopped here because this is open, right? Therefore, this device is handled fast. Okay, that this device gets the interrupt acknowledge fast. Okay, and after that device has been taken care of by means of that interrupt handler, that means its corresponding interrupt handling has been executed and the actions has been taken for which the device has interrupted, only then this is closed. Okay, say this is closed. Right now, since this is closed, the interrupt acknowledge now can flow through it. This didn't want to interrupt, therefore it flows through it, and then only it comes to this kth device. It is open, that it cannot, the signal cannot proceed any further and now this device will be taken care of. Okay, this is called daisy chaining, and here you can see the situation essentially is like this, that the device which is closer to the CPU in this daisy chaining, right, is have the higher priority than any device which comes after it in the daisy chaining. Okay. Now, this is another way by which we can accommodate more than one devices, right? Now it's called the daisy chaining. Name comes from that you have heard possibly the daisy flowers. Okay, it's possible to make, for example, a chain by just cascading the daisy flowers. Okay, from that the name has come. Okay, this is daisy chaining, right? Now you see this daisy chaining concept along with these multiple interrupts, okay, where each interrupt line can be daisy chained, that acknowledge line can be daisy chained, we can accommodate as many devices as we can, as we need to be interfaced to the CPU, right? Therefore, there need not be as such any level, any restrictions on the number of devices that can be connected to the CPU, okay, except possibly that how many such fast devices are connected so that the bus doesn't get choked. Okay, right. And once more, the concept of naturally either it is daisy chained or say, for example, that multiple interrupt levels. This interrupt mask and interrupt levels, along with that interrupt enable disable bits, should control that which device will be executed, okay, which will be handled fast, okay, handled in priority over others, right? Now let us see that there is one more device which we call the interrupt controller. Okay, this interrupt controller also helps in connecting many devices to the CPU, right? Here we have seen the daisy chaining, right? Here, say for example, we have just simple once more one interrupt line, simple one interrupt line. This is called a interrupt controller. It has say 0 to 7, 8 lines, right? To this we call this, input lines. There are other lines, we are not bothered about them right now. These are interrupt input lines, okay, and say therefore we can connect at most 8 devices over here. So device number 0 to device number 1 from the device interface here. The first one is connected to IR0 and so on, the second one will be connected to IR1 and so on, right? Now if any device wants to interrupt, then it puts this interrupt line, its own interrupt line high. On getting this interrupt line high, that interrupt output is generated by that interrupt controller to the CPU, okay? CPU on getting this interrupt and on finishing the execution of the present instruction sends an interrupt acknowledge to the interrupt controller. On getting that interrupt acknowledge to the interrupt controller, as I was telling, that interrupt controller then puts into the data bus the address of the interrupt handler corresponding to the device, right? Let me repeat, say so this particular device wants to interrupt, it puts this line high. On getting this line high, right, this interrupt controller puts this line active. On seeing this line active, if the CPU can accept that interrupt, on executions of the present instruction cycle, interrupt acknowledge is sent. On getting that interrupt acknowledge, the device, this interrupt controller puts into the data bus the address of the interrupt handler of this device, which address is now taken by the CPU, and the control goes to the interrupt handler at that address, and that interrupt handling execution starts. Okay, this is the situation in the case of an interrupt controller. here is an interrupt controller that can handle 8 devices. That interrupt controller, one can at the same time prioritize, okay, the different devices. That means which one have higher priority than the other. That priority can be decided by that interrupt controller. Accordingly, that interrupt controller takes care of the situation. Okay. Now here, in the case of a daisy chaining, as you have seen, right, there we can go on daisy chaining many devices. We need not restrict to 7. Here, what we do in that case, the interrupt controller, if the devices is more than 8, right? What we can do and is possible is this, that we go for 2 levels of interrupt controller. This is an interrupt controller which called the master. Here, these are other interrupt controllers, okay, which we call slave, right? Now here what happens, you see, the devices are connected, okay, to the slaves, right? For example, I have shown one particular device interface that is connected to the slave, say to IR0. Now on getting this interrupt at this point, right, interrupt request at this point, this slave interrupt controller then sends a signal to the master interrupt controller here, okay. Now on getting that interrupt controller request here, the master then sends an interrupt request to the CPU, okay. Now CPU once more, when it can acknowledge this interrupt, okay, issues a interrupt acknowledge signal to the master, right. Now as this interrupt acknowledge signal, it's not only it issues to the master, the interrupt acknowledge signal is also issued, also is connected to all the interrupt acknowledge of the slave, okay, all the slaves, right. Now on getting an interrupt acknowledge from the CPU, okay, this master then sends this green line signal, we call that slave select, that will select that particular slave whose interrupt has been honored. For example, here this particular interrupt has been honored, okay, and therefore you see that, so for example, if this be number 1, the SS will contain number 1. It's a 3-bit line indicating that it can choose any of the 8 devices here. This particular SS signal will choose this interrupt controller, slave interrupt controller, and therefore on getting that interrupt acknowledge, since this interrupt controller has been selected, this interrupt controller then puts the corresponding device address onto the data bus. Okay, let me repeat once more. So this is a device interface connected to a slave, say. It has requested the interrupt. This request is transmitted to the master. On getting this request, it then transmits to that CPU. On getting an interrupt acknowledge, right, master sends a signal to the corresponding slave interrupt controller, whose interrupt the CPU has now accepted. Right. Interrupt acknowledge signal from the CPU through the control bus comes to all the devices. But here interrupt acknowledge comes from the CPU. Here the SS signal comes from the master. Then this particular interrupt, slave interrupt controller is selected corresponding to this device which had requested that interrupt. Okay, that particular interrupt handler's starting address is thrown into the data bus, and therefore control essentially goes into that particular interrupt handler, because now the CPU takes the address from this data bus and sends the control to that particular routine whose address is contained in this data bus. Okay, therefore you see that if we here this way we can accommodate 64 such devices, which is sufficient in most of the applications with a single interrupt line. Okay, here it's a single interrupt line, and you can see that the entire arrangement, either the daisy chaining or the say the multiple level, two level of interrupt handling, okay, can be combined, okay, as and when the opportunity is there and is necessary, right? Now, let us now a little bit elaborate on that interrupt handler addressing. We are saying that this is vector interrupt. Now, this vector interrupt, by vector interrupt we mean that the control, either the controller or the device interface, as is the case if there is a single interrupt, okay, single device, puts the address of the interrupt handler on the data bus, right? Now, this can be direct or can be indirect, okay? So, for example, in the case of a direct, the address, for example, that interrupt handler, the address, that 5262 will be directly thrown into the data bus, and that interrupt handler execution will start from here, okay? Interrupt handler and possibly return from here. If it's indirect, in that case, the address, say, 104 will be thrown, which contains the address of that interrupt handler. In that case, the control will come from here to this, okay, and the executions of the interrupt handling will start. Therefore, the control comes via indirectly via the content of another memory location. Now, generally, these vectors are assigned certain predefined locations in the memory in the architecture of any computer. The advantage of this indirection is this, that you can dynamically bind a particular interrupt handler. By that I mean, so for example, that you want that this be replaced by another interrupt handler during the executions of a particular process, right? Simply what we'll have to do is that we'll have to change this address so that instead of coming to this interrupt handler, it will come to another interrupt. I mean, interrupt handler which is in some other location, either here or away. Okay. That way, we have an advantage if we have that indirect vectored interrupt, right? Here I say that generally device interface supplies the address, either the device interface or the interrupt controller that supplies the address. Okay. Now, this is so far as that interrupt driven IO handling is concerned. Okay. Now, let us now discuss another IO transfer mode, which we call that, oh sorry, it's not this one, that direct memory access. Okay. That can be in cycle stealing mode or it can be in the burst mode. Let us now discuss that mode, the direct memory access mode. Now, I am showing here a simple diagram for the direct memory access. Now, the direct memory access, as the name implies, okay, that a controller should be able to access directly the memory. Here you see that I have shown this diagram. Here is a CPU. This is our DMA controller, direct memory access controller. Here is a device which has that interface, okay, and here is the memory. Now, all of them, I mean, direct memory access controller as well as that interface for the device, that either can be memory mapped or can be IO mapped. Okay. Now, let us see the case of a direct memory access what happens. In the case of either program controlled data transfer or say for example that interrupt control data transfer, the CPU ultimately has to come into the picture for the data transfer, which means essentially that whenever the data transfer question comes, okay, the CPU through execution of an instruction inputs the data into one of its register and then that data is transferred back into the memory. So a path from this comes to the CPU and then ultimately goes to them. That's the path of the data. Okay, that naturally is a time-consuming process, and if we have to transfer a block of information, a block of data, then it is not necessary that CPU should come into transfer of every word or every byte of data. Why not let there be a controller which will transfer all the bytes or the words from a device interface, okay, into the memory and then reports to the CPU that the data transfer is complete. Okay, such a controller is called a DMA controller. Okay, now it can be this way. I mean, either that a device, from the device it is coming to the memory, or from the memory it is coming to the device. It's either way, like that other devices that you're talking of. Either we can talk of an input device, whatever discussions we made are true for input device or an output device. Okay. Now let us see how the DMA controller works. Now you see the DMA has that address connected, address bus connected, data bus connected, and from the control bus, which has been shown in the red, okay, IO read, IO write, memory read, and memory write all are connected. Here, this interface, we are assuming that it is IO mapped. Therefore, IO read and IO write is connected here. Naturally, data bus should be connected. And to choose this interface, address bus also should be connected over to here. And as you see, that since it's memory, the memory read and memory write signals are connected. The address bus is connected, and data can be both ways. Now, let's see how the entire DMA controller works. Okay. The CPU first puts the address into the DMA controller from where or to where in the memory the data has to be transferred. Let us assume that it is from the device interface to the memory. Okay. Therefore, the address of that memory location where the data has to be transferred is put into that address bus by the CPU. Okay. Then the count is placed. That means how many data bytes or data words are to be transferred. Okay. That count is kept here. So it may be half K, 1 meg, whatever it is. Right? After doing that, okay, then the CPU tells the interface that the device can start working, or it can tell the DMA that the device can start working, and the DMA tells the interface that the device can start working. Now the device, what it does is that it now say data is coming in. As the data comes in, 1 byte of data comes in, 1 byte of data, so 1 word of data is ready. It requests, it puts a request to the DMA controller. So 1 byte data is ready. It requests DMA controller DRQ that 1 byte is ready. On getting that information that 1 byte data is ready, the DMA controller sends a signal which is called the hold request, okay, to the CPU through an input which is called the hold. Okay, that means the CPU then, the DMA then tells the CPU to hold. Now on getting hold, after some time, and what that time is we'll talk about, that a hold acknowledge signal comes from the CPU, okay, to the DMA controller, that hold acknowledge. On getting that hold acknowledge, right, the DMA controller does this. Now, as the hold acknowledge is issued by the CPU, CPU leaves control of all these 3 buses, okay, the system buses, right, system bus. CPU is a master of the system bus all along, okay, until and unless CPU relinquishes on its own the control over the system bus. Now, here is a situation where the CPU relinquishes the control. That means as the hold acknowledge signal is sent, CPU relinquishes the control over the system bus, and the DMA controller takes immediately control of the system bus. It then does this. It then sends an IO request, okay, IO read request to the IO interface and a memory write request to the memory, okay, so that the byte and that memory address is sent from this address register, so that now the memory knows that a memory write signal has come, it has to write something to the memory. The address of that location is also known, okay, and on throwing this signal, the DMA controller then sends a acknowledge signal to that interface. On that, the data byte is thrown into the data bus and comes into the memory. Let me repeat this, okay. That hold acknowledge comes, the control of the system bus is released by the CPU, DMA controller grabs the control, it sends the address where the data has to be written, okay, since I've said that is an input device written into the memory from that address register here. It sends a memory write signal to the memory. It sends an IO read signal to the interface of the device, telling that particular byte has to be read from here and that to be written into the memory location pointed to by this address registered here, and the entire transfer takes place from that interface, okay. For that, that device acknowledge, de-acknowledge signal is sent to this interface, so that on it the data is thrown into the data bus. And after the transfer is over, the interface to DRQ once more reports that the data transfer is over, okay. Then the DMA controller through hold request once more send the CPU that the data transfer of 1 byte or 1 word is over, that hold acknowledge is withdrawn, CPU gets control back of the system bus and the program starts getting executed. The program that was being executed starts getting executed once more at the point of interruption, okay. And this is how a DMA controller works, right? Now you see that 1 byte transference, CPU need not get involved, okay. Had it been, say, programmed on IO control mode, the data would have come here through an instruction execution. It needs an execution of an instruction, okay, which means several cycles, machine cycles are involved. Then it is a memory write operation. Once more, several machine cycles is involved, and it's quite a time-consuming process to transfer 1 byte of information by either program control or by interrupt-driven mode, okay. But here, you see the CPU just relinquishes, and within 1 machine cycle, okay, the data is transferred from here into here, okay, without CPU getting involved at all. Only CPU does is that it releases the bus for some time, okay. Now the question is that when this hold, on getting a request from hold, when the CPU issues that hold acknowledge, right? Here we have, let's come back once more to that instruction cycle. Okay, here is the processor cycles, the fetch instruction, decode, fetch operand, execute instructions. The machine cycles or the processor cycles goes on. At the end of an instruction cycle, that interrupt takes place, okay, at the breakpoint. The DMA breakpoint is at the end of every processor cycle. You see, after the fetch, if there is a hold request, after every such processor cycle, the red arrows, at every point, if there is a hold request, the CPU will release the bus. You can see here that on a hold request, the hold acknowledge will be, can be given at these points, because you know at these points CPU has completed the execution of one complete processor cycle, okay, and therefore the bus is no more in intermediate state. The bus has to change status from this cycle to that cycle, and therefore in between, okay, the DMA can just steal a cycle, okay. For example, essentially what is happening here, you see that, say at this point, as if the DMA is stealing a cycle without CPU almost not aware of it. Just a single cycle is stolen and one byte or one word is transferred. Okay, and that is why we said in the beginning that the direct memory access, it can be in the cycle stealing mode or it can be in the burst mode. Now the burst mode is, instead of just sending, as the control is taken by the DMA at this point, instead of just sending one byte, say a number of bytes is simultaneously transferred. Okay. How many number of bytes will be transferred? That will be dependent upon the count. Address is the beginning of the byte, and as a byte is transferred, the address is decreased, right? Now, change that on getting the count 0, that the DMA assignment is over, the job given to the DMA controller at this moment is over, then an interrupt signal may be sent to the CPU, telling the CPU that, right, that the DMA function is over. Okay. On getting that interrupt signal from the DMA controller, the CPU now can go to that interrupt, corresponding interrupt handler. Okay. Now you see, let us see that in the case of a block transfer, okay, what happens in the case of a DMA? This is a programmed I/O we have seen, interrupt driven I/O we have seen for the block transfer. Here, the issue read block command to I/O module. Here, this I/O module is essentially both the I/O module and correspondingly the DMA controller has to be set, right? Now, on getting, then the DMA goes on transferring the data. On end of transference of the total block of information, either in the burst mode or in the cycle stealing mode, but the CPU in the meantime can go on doing its own work. On completion, the interrupt comes, then its CPU reads the status of the DMA module to check whether any error conditions in between has taken place or not. I have not shown over here any error status register. Naturally, there should be some status register which will show that whether the data transfer is complete, successful, or some error has happened, etc. The CPU checks that, right, and there is error condition. Naturally, it jumps to an error handler routine. There's no error, then it goes on executing the next instruction here. That is the DMA mode of data transfer. Okay. One important thing that I should say, that a DMA controller, instead of just controlling one device, whether it is input or output, it can control more than one devices. For example, a typical figure can be, say, that a DMA controller controls 4 such devices, right? Now, you see, therefore, we have discussed all 3 modes of data transfer, which has been more or less standardized, okay, in the last few decades. Okay, the program data transfer, interrupt driven data transfer, and direct memory access data transfer. And you can see, you can also feel that DMA is generally done for devices, okay, or say some input that is coming from outside at a very fast rate. Okay, generally that DMA is engaged. Now, apart from that I/O data transfer, okay, I would like to discuss few things which are also important and which involves physical interrupt and which I will need for later on discussion. One is that there may be some interrupts hardware generated within the CPU, right? The purpose of the interrupt, you see, is to go to a handler and then come back at the point of interruption. Now, this hardware generated interrupt can be on any exceptions. For example, say the ALU is doing a division operation. Say divide by 0, that ALU itself can raise an interrupt. Okay, on getting an interrupt, it goes to the interrupt handler. What the interrupt handler does there is that it reports an error that a division by 0 has taken place. Okay, and such on getting that, right, corrections can be taken. That means user can be told that this is the status of your program, a division by 0 has taken place, a runtime error detection, so to say. Now, it can be single stepping, right? We told about the processor status here. There can be another bit So for example, here, so single step. So if this is 1, that means that at the end of execution of every instruction cycle, an interrupt will be generated. Okay, so single stepping, if this bit is 1, which means that at the end of every instruction cycle, the CPU will be executed. And you can see that this is a very good facility if you have to debug. Okay, so for example, you do not know what is happening to your program. If you want to single step through your instructions to see what is exactly happening, then this single stepping bit can be set, right? Another interrupt can be on power failure, that the power has failed, that your UPS has informed that input power has gone, right? In that case, a status saving information, a status saving actions can be started automatically by means of that interrupt handler. And power failure is generally unmaskable interrupts. As I said, that the interrupts can be masked, okay, and either by mask bit or by level situations, okay, or by enable disable. But there are some interrupts which are unmaskable, okay, which means, for example, power failure, it should be unmaskable. Nothing should mask it. All corrective actions have to be taken, okay, all saving operations have to be done, and that is why it's called an unmaskable interrupt. Now, these are some hardware generated interrupts. There can be some software interrupts also, okay, like say subroutine, which are inserted into the program to have a subroutine jump. We can insert into the program that some software interrupt instructions. Okay, these are basically instructions. Okay. Here, for example, SWI is a software interrupt. On execution, it will move to a software interrupt, possibly vectored. Okay. Similarly, trap is a software interrupt instruction. If while executing a program, if trap instruction is executed, then it goes to interrupt handler. So restart is another RSTN. For example, the RST is an instruction. Depending upon this value, at which location that interrupt handler is, okay, which particular interrupt handler it will go, that is determined by N. Okay. Therefore, the software interrupts, as we will find, that will be very useful, okay, later on when we will be doing, say, supervisions or say, monitoring or controlling operations of the system, right? That we'll see it later on. Now, this is so far as our software interrupts are concerned. One just more thing that I would like to mention, though I will not going to details, is beyond the scope of our lecture. Okay, is that I/O processor. Here, that this is sometimes called a peripheral processing unit or I/O channel. This can execute I/O instructions on its own, so it can handle I/O operations independently and communicates to the CPU as needed, which means these are more powerful. The processor themselves of limited capability to handle I/O and communicate to the CPU. Right? Such processors are sometimes utilized for a big systems, okay, to handle I/Os. Okay. Now that is all so far as our modes of I/O transfer is concerned. Okay. Thank you.